How does one know if an arrestor is entering its end-of-life phase? Typically, there are no visible signs that an arrestor is starting to deteriorate. An arrestor's age or type offer little help in assessing its own functionality. There are probably more than 100 million arrestors in service today, many of which date back as far as 1950. With this diverse arrestor population, it has become imperative to develop other means of assessing the health of an arrestor. This video is about the popular assessment method, thermal imaging. Over the life of an arrestor, it can be exposed to very harsh physical environments, as well as harsh electrical environments. Many of these events have the potential of damaging the internal or external components of the arrestor, to the point that an end-of-life event can be near. For instance, if one of these events leads to a damaged seal, moisture can get inside the arrestor. Moisture in an arrestor may cause the insulating members, such as the disc collar or the inside surface of the housing, to change its electrical resistance. If the resistance drops significantly, it can begin to conduct current off the system. In the process of conducting higher than normal leakage currents, it generates heat. This heat generation usually starts out low and increases with time. Another potential source of heating in a failing arrestor is when the varistors themselves change resistance. Instead of being gigohms at their normal voltage, their resistance lowers to megohms. The reduction in resistance eventually can reach such a low level that they can heat the insulating materials around the disc to levels that burn and discolor them. In both of these examples, the arrestor will produce heat that is easily detected by infrared thermography. A third heat generator in a failing porcelain-housed arrestor or hollow core polymer arrestor is from internal partial discharge. This is usually found in higher voltage station class arrestors and occurs when voltage stresses are too high inside the arrestor due to rain or snow on the outside of the arrestor. This partial discharge may not cause enough heat to be distinguished by thermal imaging, but the resulting ozone gases inside the arrestor can degrade the discs to a point where they will conduct enough leakage current to increase the temperature of the arrestor. Even though gapped silicon carbide arrestors have not been manufactured in many years, there are still millions of them in service today, and many are nearing the end of life. Even with this old technology, a long-term failure will result in a temperature rise of the arrestor. A common cause of heat is degradation of the gap resistor or degradation of the material that holds the gaps apart. This material was designed to conduct small amounts of current, but as the arrestor ages, sometimes the currents increase. This increase in conductivity along the gaps will produce heat that is easily detected by infrared thermography. When using thermal imaging to monitor the health of arrestors, there are several guidelines that can help improve the outcome. Here are a few. The first recommendation has to do with the time of day. The time of day the reading is taken can make a big difference in accuracy. Since the temperature of an arrestor mounted outdoors is in constant state of flux due to the effects of the sun, measuring the temperature between midnight and sunrise will give the most accurate temperature reading, which in turn will result in the most accurate health indicator. Our second recommendation: for optimal assessment of the arrestor, its temperature should be compared to those of partner arrestors on the line. The absolute temperature of the arrestor is not as important as the difference between similar units. Although comparing the arrestor's temperature to ambient may reveal an issue, it also can be misleading. Our third recommendation has to do with frequency of observation. Partner arrestors on the different phases of a line should have temperature readings that are very close to one another. If this is true, an observation frequency of approximately every 6 months can be used. If this is not the case, the course of action depends on how great the temperature differential is. For a delta T of 10 degrees C or greater, the arrestor should be removed immediately if possible or monitored very closely. Since a single temperature reading only indicates an issue, subsequent readings are necessary to determine if the issue is critical or not. It is suggested that the observation frequency be 1 week and then increase to a month if there is very little change over a few readings. However, if the differential in temperature increases, the arrestor should be removed as soon as possible. There are no definitive times for when an arrestor will fail once it starts to run hotter, so the owner must define how critical a failure will be and the necessary actions to be taken. Our fourth recommendation has to do with equipment. There are numerous thermal cameras available on the market today, and most are excellent for this application. There are 2 features, however, that we recommend. The first is a long-distance lens so that only the arrestors are in view. The second is a minimum resolution capability of 0.5 degrees C. If the arrestor is in a highly critical location, the installation of a live streaming thermal imaging device should be considered. Although thermal imaging is an effective way to monitor the health of an arrestor, there are several issues that need to be kept in mind. The first is, to measure the health of a surge arrestor using this method, the arrestor needs to be energized. If the arrestor has been de-energized for some time, it will not show a temperature differential other than that caused by the environment. Secondly, sun load or a transformer radiator can cause a false reading. Third, the equipment can be expensive. However, if it is used extensively, it can pay for itself quickly. The fourth is that an arrestor that shows a warm profile can be moments or years away from failure. It is difficult to tell with one reading. And finally, number 5, because this is a periodic reading, failure can occur between readings without notice. If this were a constant reading, a warning alert could indicate a failing arrestor. In summary, the use of thermal imaging is a very efficient method of determining the health of an arrestor. Because all systems are subjected to unexpected high surges, all failures cannot be detected or avoided. However, users of this method can reduce the likelihood of experiencing an unplanned outage by identifying arrestors that are starting to show signs of end of life. This video has been sponsored by the NEMA 8LA Arrestor section, and they encourage you to keep on learning.